Hello everyone, I'm Jaegol Chu, one of the instructor of this Machine Learning for Data Science course. So this is the second lecture in the 13th week on deep learning. So we will continue studying convolutional neural networks. So in this lecture, we will discuss a little bit of details on this convolution operations. And also we will consider this zero padding and the filter and the activation sizes as well. And then in the previous lecture, we studied convolutional neural networks by using a toy example. But in reality, our input image has this kind of size. So for example, suppose our input image has the size of 32 by 32 in terms of width and height. But also, since we are often dealing with the color image, and thus we can view them as having the depth of 3, which means each of these 32 by 32 matrices are concatenated into three different slices, and each slice will contain the value ranging from 0 to 255, representing R channel or red channel or green or blue channel, and that way we obtain the depth of 3. And in the case of our convolution filter, suppose our filter size is this 5 by 5. Okay, so in this case, since our input image has the depth of 3, and then we have to think of our convolution as having also the depth of 3. So it means our convolution filter is not just defined as this two-dimensional array, but also instead it has to be defined by this three-dimensional array. Okay. That considers this depth of 3. Okay. So in total, 25 times 3, which is 75 different coefficients are contained in our single convolution filter. Okay, and so this is a kind of our convention, but we always think of our convolution filter as having the same depth as the input image depth. Okay, so that way we always assume that our filters always extend the full depth of the input image volume. And then when applying our 5 by 5 by 3 filters into this particular position, and then considering this a center pixel, we can think of the matching score as a scalar by applying this filter onto this particular position in our input image. Okay, and then it can be viewed as a kind of inner product or elementwise multiplication and then summing them up as we saw in the previous example. So we have in total this number of values defined in our filter, and then we will perform the element-wise multiplication on each different 75 values, right? And then that way we can define this dot product on this 75 dimensional vectors, and then we can consider this bias term as well, and then it can be represented in this form: W transpose X plus B. So W transpose, or this W vector, is a 75 dimensional column vector that are obtained by our 5 by 5 by 3 filters. Okay, and then the pixel values corresponding to this particular region can be represented as we are considering this a transposed version of this vector, and then this one will be transposed, and then our vector x can be represented as a single column vector that are also obtained from all the values contained in this particular region of our input image, and then reordering them into this single column vector as having 75 dimensional vectors. Okay, and then we can perform this inner product, and that is corresponding to this element-wise multiplication, and then sum them up, and then we add some bias term. Okay, and then previously in the previous lecture we performed this element-wise multiplication and then divided it by 75 to compute the average value. But typically in the standard convolutional neural networks, we skip this part. Okay, so we do not divide this by the total number of elements. Okay, but instead we consider this bias term. Okay, and so this bias term will be applied on every different position that we applied our convolution filters to different part of an image. Okay, so that way the resulting activation map will be having this 28 by 28 by 1 as depth value. Okay, and the reason why we have a 28 as the height and width value is because we have 32 by 32 as an image size, right? And then if we do not consider something called a zero padding that we briefly learned in the previous lecture, and then the leftmost position will be here, and we will have this, right? And then we can obtain the this activation map around corresponding to this position will be corresponding to the input pixel positioned in this place, right? And then it will be let's enumerate them: 1, 2, 3, 4, 5, and then the rightmost part will be 2, 3, 4, 1, 2, 3, 4, and then it will be 32, 31, 30, and 29, 28. Okay, and thus the activation maps width will be 32 minus 5 plus 1, okay, which is 28. So that way we will obtain this activation map size as 28 by 28 for width and height, and then the depth will be just 1. Okay, and then suppose we defined another filter as having the same size. Okay, so in one convolution layer we defined a multiple different filters but with the same size, right? And so suppose we have a second filter having this size, and then that will also generate this size of an activation map also with the depth of 1. And if we have a 6 different filters in one single convolution layer, and then each of these 6 different filters will give a depth of 1 for its activation map, and then the activation size will be 28 by 28, and then altogether we will have this size of an activation map of 28 by 28, but also the depth will be 6. Okay, so we basically concatenate our activation maps along the depth directions, and that's how we obtain one single 3-dimensional activation map. Okay, and then in the previous lecture I mentioned that after applying conv layer, we always apply this ReLU in order to just apply nonlinear transformation. And then this nonlinear transformation will not change the activation map size. So given this activation map as an output to output from the convolution layer, and then after applying the ReLU, this activation map will, the size of it will not change, and thus the size will remain the same. And then now let's consider the situation of applying another convolution layer given this input activation map. So we view this activation map as just a kind of typical image representation, as having the width and height as 28 by 28, but now we have a depth of 6 instead of this 3 as an RGB kind of channel or depth. So in this case, suppose the filter size was also 5 by 5. So we have this 5 by 5 filter size, but we studied that the filter size, the depth of filter, should always extend the full depth of our input image, and thus our filter should also have the depth of 6, which is the same as this number. So that's how we define each of our convolution filter in this convolution layer. Okay, so each filter will have this size, and suppose we defined 10 different filters to detect 10 different patterns from this input activation map. And then altogether, from this width and height of 28 by 28, the width and height will be reduced to 24, which is 28 minus 5 plus 1, right? And that's how we reduce the width and height. But also in the case of a depth part, since we have 10 different filters in this convolution layer, and then we will have 10 different activation maps that has the size of 24 by 24 as a single, as a thin matrix, and thus the depth will be 10 in this case, which is the same as the number of filters that we have in this convolution layer. So in this manner, we can apply this conv-ReLU and conv-ReLU and conv-ReLU and so on. And optionally, we can perform this max pooling in the middle. And as we go through this convolutional operations layer by layer, we can see that in the first convolution layer, it mainly detects some low-level features, such as this kind of edge representation, and sometimes some particular color of green or some pink or magenta colors and so on, and some other different edge representations. So these were trained or learned filter patterns from this image recognition tasks. But in the second layer or the third layer, our filter pattern, although it was like 5 by 5 size of a filter patterns, but these patterns were defined on the activation map. This activation map was containing the matching score on these given filters used in the previous layer. And so from this input images, the patterns defined in this second layer convolution can be kind of a composition of the patterns of the first layer and then also the patterns in the second layer. And that way, if we recover or reconstruct those input image patterns that this convolution filters are trying to capture in this second layer, and then these filter patterns can have these kind of shapes, which is a little bit more complex pattern. So in this case, it tries to capture some interesting color patterns, where the middle part is capturing this green pattern, and also the peripheral parts as containing those pink colored pattern. Okay, and also in the previous case, it detected this straight shape of this edge representation, but in the second layer, it can have this a little bit slanted or a little bit curved patterns as well. And then in higher levels of convolution layers, it can have much more complex patterns, which looks like a little bit of maybe some eyes and yeah, maybe some mouse of a particular animal and so on. So that way, our convolution layers will be able to capture more complex patterns in this later convolution layers. Okay, and then overall, we go through this conv-relu, and sometimes we perform this pooling and conv-relu, and pooling and so on. And then we transition to this fully connected layers. And then after all, we obtain some categorical scores by applying maybe softmax layers, given these multiple different categories that we have to classify into. Yeah, and then given a particular image, and then we consider the scores for each categories, and then we obtain the most likely or most probable classes as our prediction label. Okay, and then we can see that, yeah, so these are different activation maps by applying different filters. Okay, and then this is one particular activation map, and then the other, and so on. And even though they are shown, they are aligned this vertical pattern, but they are concatenated along the depth directions, as we saw in this example, right? So different activation maps will be concatenated or stacked along this depth direction. Okay, and this was a convolution layer, and then let's think about this zero padding. And in practice, it is common to add this zero padding along the border, and the main reason for adding this zero padding is to maintain the activation map size to be the same. I mean, in terms of the width and height. So suppose this one is the original input image, and then 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So originally it has the width and height as a 7 by 7. And suppose our filter size was 3 by 3. Okay. In this case, if we do not use a zero padding, and then, yeah, this is the left and the uppermost filter positions, right? And then it will produce the matching score corresponding to this pixel. And thus, we cannot obtain the matching score corresponding to this or this or this pixel positions, right? And thus, in order to obtain the same number of matching scores corresponding to the total number of pixels that we have in this 7 by 7 original pixel size, and we have to zero pad to align our filters in this manner. So in this case, the center position of our pixel is exactly aligned with the left and the uppermost pixel values, right, in our original image. And in to this end, we have to zero pad in this manner. Okay. So if our filter size was 3 by 3, and then we will have to pad just one more pixels to the left and to the upper part. Okay, so in this case, the activation map size will be the same even after we apply this 3 by 3 filter. So in general, if we apply the filter size as 5 by 5, and then, yeah, we have to align the center position of our filters with the left and uppermost pixel position. And that means, yeah, our filter will be having this size, right? So that way, we can apply this 5 by 5 filters by aligning this center positions with the top left pixel positions. And that means we have to zero pad 2 columns and 2 rows. in addition to the original image. And so zero padding size will be 2. Okay, and then also similarly, of course, to the right and to the bottom and so on. So they should also have the same zero padding size of 2 columns and 2 rows in the bottom part as well. And then in the case of filter size of 7 by 7, and then we put the center pixel here, and then we have 3 more pixels to the left and to the upper part, and thus we will have to have a zero padding with the size of 3. The reason for this zero padding is to avoid this shrink the size of our image or decrease size of an image. So if we do not apply the zero padding, and then in the previous example that we saw in this case, if we apply this 5 by 5 filters, and then the input image size will be reduced by the amount of 4. Okay, so in this case, this shrinked image size will be done too fast, and in this case we may lose some spatial resolution or some meaningful information. So basically we are losing some information on these edge positions in our input image because we cannot apply our filters to this exact edge pixel positions, right? And so it can lose some information unintentionally, and thus we apply this zero padding in order to avoid this situation. Okay, and then let's consider some number of parameters and the number of activation. So suppose we have this input volume as 32 by 32 by 3, and then suppose we applied this filters with the stride size of 1 and zero padding with 2. And then what will be the output volume size, which means what is the activation map size. And so the width and height was 32 by 32, and then the filter size was 5 by 5. And then we added the zero padding with the size of 2. And then it means the width and height will remain the same, right? And then the applying these filters, and then we apply the 10 different filters, and then each filter will generate one single matrix having the size of 32 by 32. And then the depth, in terms of the depth wise, and the number of depths will be exactly 10, because each 32 by 32 matrix will be generated by each different filters, and we have 10 filters in total, and then the depth will be 10. So this one will be our output volume size or activation map size. Okay, and then what about the number of parameters in this layer? So what is the parameters that we have to determine during our training process? So the parameters are all contained in our filters, and in the case of one filters, it will have 5 by 5 as width and height. And also, what about the depth of this filter? So depth should be the same as the input activation map, and then the depth will be 3 accordingly. And then for this number of parameters contained in our each of our filter, and then if we remember how we computed this activation map, it was shown in this form. And then 5 by 5 by 3 will be reshaped into one single column vector, and then change it to a row vector, which means which is represented by this W transpose, and then X will be the input pixel values in a different positions that this convolution filters are applied. And then we had additional bias parameters, right? And then for each of this filter, for this particular filter, we will have one single bias term as a scalar value. And then we will have 10 different filters, and then this bias will be applied for different filters, and thus this one will be the number of total parameters defined in one convolution filter, and then we have 10 different filters, and this is the number of parameters in this convolution layers. Okay. And then let's consider this a pooling layer by considering these depths carefully. And suppose this one is our activation map. So width and height was 224, 224, and then we have a depth of 64. And then the max pooling, or this pooling layer, will be applied each depth of an image. So suppose we applied 2 by 2 window size of a max pooling, and also the stride was 2. So in this case of a max pooling, this window can be viewed as just a single matrix as a depth of 1. And so this filter, or this max pooling window, will be applied depth wise. So it will be applied in the first depth of an image, which we call a channel. So first channel will have this pooling operation, and that way you will have 112 and 112 as the activation map size. Okay, and then we perform this pooling per each channel of these 64 different channels, and then we will have the same number of channels. And this is how this max pooling, or this pooling layer is applied. And then it is also called a downsampling, or kind of resizing of this input activation map. Okay, so it doesn't change the depth at all, but it will change, or it will basically reduce these activation map size in terms of its width and height. Okay, so we already studied how this max pooling is done. So we basically pick up or choose the maximum values from this window that was applied. Okay, so this is the end of our convolutional neural network. And in summary, our class covered the details of this convolutional operations, and then zero padding, and also we studied the filter and the activation map size in more detail, in more realistic example or scenarios. And yeah, thank you very much.